Now, what we're going to look at now, well, the name of the chapter is Electrical Properties. So this is now, if you remember, I said the course has 6 parts to it. So this is the next part of the course. So we can just call it part 2, Return of the Physics, Electricity. Let's see. So you have done electrons in chemistry. Have you done the charge of an electron?
Yes.
Yeah. Now what have you done with Lorraine about charge? Just that it has a charge or anything else?
How to get it?
What do
No.
you
You're
mean?
talking about the charge of the atom.
Yeah. Or even with the atom, yeah. So what do you know about charge from chemistry? Do you know, for example, the unit?
Yeah, Coulomb.
Coulomb. And do you use that unit in chemistry?
No.
No. Do you just say like +1, -1?
Yes.
Yeah. So an electron has a -1 charge and a proton has +1 charge then. Okay. What we're going to do is just start off with charge then. The definition for charge we won't do just yet. It's kind of a complicated definition. But I'm glad that you already know about charge in chemistry. So in chemistry you learn that in your atom an electron has a -1 charge. Come on. Hang on, let me... Oops. And you probably already know from chemistry that if the charges are the same, what happens? No, if they're both positive. If you have 2 things that are both positive, what do they do? Yeah, what's the verb? Repel. And if they have opposite charge, they attract them. Okay, so I will just say that an electron has a negative charge, a proton has a positive charge, and the unit we use I don't think they get the definition. They don't. Yeah. Whoops, sorry. And the latter is big C. Now, the definition here. Yeah, this is page 3. The definition, I think, is not so helpful. So what I'm going to do is I'm going to give you 2 definitions. The first definition is just to help you understand what a Coulomb is. The second definition is the formal definition for the exam. So the first definition is like, you could say, the informal one. So you could say an electron has a charge of, let's see, come on, hurry up, 1.6 times 10 to the minus 19 coulomb. So therefore, minus 1 coulomb of charge is the same as, come on, yeah, the charge of, can I just have a calculator for a second there?
This is 9.
Yes, this is yes.
So that definition, like I said, it is the informal definition, which I kind of like, because it gives you something to picture. If I said something has a charge of -1 coulomb, it's like saying, oh, it has the same charge as that many electrons. And I like this definition because I feel like the charge of an electron is like a basic unit of charge. You know, you never really deal with things so much smaller than this.
How did you calculate the -1?
What do you mean minus?
-1 coulomb.
Oh yeah. Well, I know that the charge of one electron is that many coulombs. So if I just do 1 over that number, in other words, that's how many electrons I need to have 1 coulomb of charge. And like I said, this is kind of the informal definition. It just gives you a picture of how many electrons you need to have a charge of -1 coulomb. Okay. Now, what's the charge of a proton? It's the same as an electron. It's just the opposite. Yeah. So also you could say a charge of 1 positive coulomb is the same as having 6.25 times 10 to the 18 protons. It's the same amount of charge. So my point is, the charge of an electron is very, very, very small. Okay, so that coulomb is kind of a big unit for charge. And often you end up using things in the exam like millicoulombs and microcoulombs. So coulomb is a kind of a big unit. Okay, so it is very common in the exam to use millicoulombs and microcoulombs. So I'll just say the same thing about the proton, and then I'll give you the formal definition. Okay, now time for the real definition, and what I mean by that is this is the definition for the exam. So it has come up in the exam. They said, what is a coulomb? Or define a coulomb. So this is what you would need to write for the exam. Definition. 1 coulomb of charge is equal to the charge produced, or no, I don't say the charge in a 1 amp current running for 1 second. Yes, and this is why, no. And this is why I don't like this guy. Yes.
It's not.
Oh no, I only wrote amp just because it's the first time I'm using this word. I will use A from now on. Yeah. And actually, if you buy a fuse, they might say AMP on it. Anyway, the reason I don't like this definition is because this definition relies on another term, which we haven't done yet, called an amp. So I'm not going to talk much about this. Because this definition relies on a definition for the amp, and the definition of an amp is complicated. So, what is an amp? Yeah?
Isn't there another definition, like quantity or quality?
Yeah, well, this is the thing. There's a few different definitions. I am giving you the one which they want for the exam. And then up the top is the one I kind of like. But you're right, there are other ones. Yeah. So then if you said to me, what's 1 amp? it's easy for me to say, well, 1 amp is when 1 coulomb travels for 1 second, which is bad because I can't use the same sentence for both definitions. So if you said to me, okay, what's a coulomb? I say, a coulomb is 1 amp for 1 second. And you say, okay, great. What's an amp? An amp is 1 coulomb for 1 second. Do you see the problem with this definition? Okay? So I'm telling you this for the exam. In the exam, if they ask what a coulomb is, you write this down. But I don't like this definition because I prefer to say 1 amp is 1 coulomb for 1 second. And then you say, what's a coulomb? And I say, well, a coulomb, you need 6.25 times 10 to the 18 protons, then you have 1 coulomb of charge. Okay, so this is how I prefer to explain it, but it's not what you need for the exam. So I'm just making that very clear.
So if you write the thing in blue,
You don't get any marks in the exam.
if this is correct definition.
I know, but the marking scheme is quite clear. The syllabus is quite clear of what definition to use for the exam. So you're right. I think there's nothing wrong with it, but it's not what they want. So I'm just telling you for the exam. But for understanding, 1 coulomb is that, and then 1 amp is 1 coulomb per second. It's the rate of coulombs per second. Okay? So it's a bit like the speed, isn't it? It's per second. Okay. So let's have a look at our first example then. Oh yeah. I'll just give you some letters now. So scroll down. So we use Q to measure charge, and the unit is coulombs. We use T for time, and of course the unit we use is seconds. And we use I for what we call current. So what is current? Well, current is the rate of change of charge. So its unit is amps. So for example, if I equals 1 amp, that means we have the same thing as 1 coulomb per second. That's what 1 amp is. Another unit for amp is coulombs per second. So I'll just finish by saying that here. Amp is the same thing as coulombs per second.
Coulombs thing as amp per second.
1 second, sorry. Yeah.
Coulomb amp per second.
Amp seconds. Yeah. So we actually have our first formula already. We can say that I equals the change in current over the change in time. In other words, I is charge over time. Like that's almost the definition, isn't it? So this is our first formula. Q equals IT. That's our first formula. Charge Q equals current multiplied time. I multiply T. Okay, so let's do our first problem then. Can I scroll down? Yeah, not yet. Yeah. Scroll down. Okay. So, first example. So we have a piece of copper wire. So I've zoomed in on it. Now, how big is the wire? Let's say, how long is it? Oh, well, I guess we can just make up our own example if they don't say it here. We'll just say 1 meter. Okay. So this piece of wire, we'll say is 1 meter long. Okay. And let's say this here, the area, let's say the area on this piece, we can use what they have here, is 1.1 times 10 to the minus 7. Cross-sectional area only, yeah. That's a typical value for a piece of copper wire. It's quite small, because it's just a little wire. Okay, and let's say now that there is 1 amp running through the wire. So if there's 1 amp, how many coulombs per second is that? It's 1 coulomb per second then. Okay. So now let's work out how fast the electrons are moving. So what we need to know is how many electrons there are in it. So this is also given in the question. I should actually just go back to chemistry a little bit. Why is a metal in chemistry a conductor? Why is a metal a good conductor in chemistry? Yeah, there's free electrons that can move. I think maybe you can use the expression a sea of electrons, isn't it? Yeah. So there's lots of free electrons in it. So the reason that there's a current moving through this is because there's lots of free electrons. How many free electrons are there in copper? Well, it's given in the question. So I'll tell you here. In 1 meter cubed of copper, there is 10 to the power 29 free electrons. So that's how many free electrons you have in 1 meter cubed of copper. So let's work out how much we have in this piece here. So number of electrons. How many are there? Well, first we should work out how much copper we have. So volume. What does volume equal? Well, it'll be the length multiply the area here. And that's easy because I made this number here 1. So 1 multiply this number, that'll be 1.1 times 10 to the minus 7 meter cubed. Okay, so we have 1 meter cubed equals this. So therefore 1.1 times 10 to the minus 7 meter cubed would be basically that number multiplied 10 to the 29. So it'll be quite small. Well, not quite small, but smaller. So if you multiply this number and this number, what do we get?
1.1
Sorry, 1 second. 1.1 times 10 to the minus 20.
plus 22.
Sorry, plus 22, of course. So that's how many electrons we have. Okay. Now, let's work out. Let's see what we want next. Yeah, we want to work out how fast the electrons are moving. Okay, so if this is 1 amp, it means 1 coulomb comes out here every second. And this is how many electrons we have. And what's the charge on 1 electron? I think I gave it to you earlier, isn't it? It's no. What's yeah?
1.6 times 10 to the minus 19.
Times minus
19.
19. Okay. So, isn't it the same I gave you earlier? Isn't it? One electron. No, just 1 electron.
Yeah.
Charge of 1 electron. So if I take this coulomb here and divide it by this number here, that's how many electrons must come out at the end. If I want 1 coulomb, how many electrons is that?
6.
Well, actually, I gave that to you earlier, didn't I?
5 times 10 to the power 15.
Yeah. Number of electrons that come out I want to know how fast they're coming out at. That's what I'm working to.
The speed of each
Yes, yeah. It's not really a question, it's more just a bit of theory. Sorry, so what is it? 6.25 times 10 to the 18 electrons per second. That's how many come out. So now we want to work out how fast they're coming out at. How many electrons do I have in total? Yeah, times 10 to the 29. And how many do I need to come out?
22.
Where is it? Where? Oh yeah, I should put this in a box. Is that okay so far? Yeah. So I have 1.1 times 10 to the 22 pieces of electron here, and I have 6.25 times 10 to the 18 electrons per second need to come out. So I want to work out how fast they're coming out at. Now, before we do it, if we just think about it for a moment, if there was not many electrons in the copper, and I need a lot of electrons coming out, will this mean it's coming out fast or slow? So just think about that. If I had a small number of electrons in copper, but there's a lot coming out, does this mean the electrons are moving fast or slow? Fast, yeah. Now imagine I had loads and loads and loads of electrons, but there's only a few coming out. So does this mean they're moving fast or slow? Slow. Okay. Now let's take another example. Suppose I had 6.25 times 10 to the 18 electrons coming out per second, and inside of it I had 6.25 times 10 to the 18 electrons inside of it. So that means all the electrons inside of it are coming out in 1 second. And if it's 1 meter long, how fast do you think the electrons are moving? 1 meter per second. So in other words, what I'm trying to get to is you can do it as like a fraction. Okay? You can take that number, divide it by that number, and multiply it by 1, and this tells you how fast the electrons must be moving. So can we do this number divided by that number, and you should get something really small. So what do we get when we divide it? 1.76 times this number divided by this number should be a small number.
5.7
That's,
times 10 power minus 4.
Thank you. 5.7. So in other words, we'll just round to 1 decimal place. So 6 times 10 to the
power of
minus 4 meters per second, which is 0.6 millimeters per second. And that's the result that they have in the book as well. Where is it gone? From 1 page too far. So the point of this exercise here is just to show clearly that when you have a current of 1 amp per second, the electrons are actually moving really, really slowly. Really slowly. Which
number are we dividing 6.25?
the second number divided by the first number in the boxes.
1.1.
You have electrons second, and divided by electrons to have the second, and times it by
meters
to have meters per second.
But meters only 1, so you see they're moving really, really slowly. Mohammed, I'm getting tired of looking at you in my class and seeing you not focused on what's happening. Okay, so moving really slowly. Right, next now. I'll do the formula for this really quickly as well if you need it, okay? So we start off by saying Q equals IT. Okay, and also volume equals, remember, length multiply area. Okay. And remember we also talked about how many electrons we had per meter cubed. So I'll call that N. That is the electrons per meter cube. So that means big N, which is the total number of electrons, that will equal V multiply N. That makes sense. N is how many electrons we have per meter cubed, and V is the how many meter cubes we have. But what's the formula for V? It's LA. So we get this formula NLA. That's how many big electrons we have. So what's the total charge? Well, it's how many electrons we have multiplied by the charge of one electron. So we have a formula for big N. Here it is right here. So that's NLAE. So that's how much charge we have. But we have a second formula for charge right up the top here. So if I put these two together, I get IT equals NLAE. Now, if I do a little bit of division here, I have L over T, bring the T down here, and then I have I over NAE. What's L over T? What's distance divided by time? Speed. So that's V. So we get V equals I over NAE. Oh, you're right. That's a small v, which it doesn't look like it. Speed. So let's just use this formula for my example I did, just to double check. So what was the I? What was the current? 1. And what was the N? How many electrons per meter cubed did I say is in copper? 10 to the 29, wasn't it? So 10 to the 29 times the area, which was 1.1, times 10 to the minus 7 times 1.6 times 10 to the minus 19. Can you just type that in and double check that you get the same answer? You should get 0.6 millimeters per second. Yeah, we rounded it up. So 0.6 times 10 to the minus 4.
It's the same answer.
Yes, that's the point, yeah. Okay. You might find that formula useful at a later point. So this is our second formula. The speed of the electrons is equal to this. That's the speed of the electrons.
We'll need to find the speed of electrons. The example will have to derive.
Oh no. Yes, but the formula is a bit like Kepler's law. It's not in the formula book, so it's one that you'll have to remember. Okay. Can I scroll down? Yes. So quick recap. So far we have Q. What does Q represent? Charge. I. Current. T. Time. So what we're going to do next now is big V, which is called, well, I call it voltage, but here it's called potential difference.
Could you scroll?
Yeah? Can I go down? Okay. So what do we mean by potential difference? Or we can call it voltage. You can think of it a bit like potential energy. It's a bit like this. And that's actually important to compare it to that. So let me just give you an example here. So this has potential energy. This has potential energy. This has more or less. Less. So if you want to work out how much it loses, you have to do this distance minus this distance. So in other words, you need to know this distance here. Yeah? Do you need to know how far from the Earth's surface this is? No, you don't. You just need to know this distance minus this distance, okay? That's the same thing with potential difference or voltage, okay? It's only important to know how much the voltage changes. So a bit like height. Height is important, of course, but what's really more important when we're talking about energy is the change in the height, not the height from the ground. So it's the same thing with potential difference. You're really concerned about the change that happens rather than the value. So what is potential difference? Okay. The unit is volt. And this is the definition of volt. When 1 coulomb is moved between A and B, and 1 joule of energy is released, that means there is 1 volt of potential difference between A and B. So in other words, if you take 1 coulomb from A to B and you can make 1 joule of work, then we say that there is 1 volt between A and B. So voltage has to, potential difference, voltage, it has to do with energy. So if you think about electricity, the charge is moving around. So voltage, it tells you how much energy you have, how much work you can do. So if you think about it, here's my coulomb. Okay? If my coulomb is here, and it moves down to here, and it gives me 1 joule of energy, then we say there is 1 volt between A and B. Okay?
So volt equals to
You could again get the formula out from that, yeah.
So coulomb joule.
We don't actually, yeah, we always write as volt. We'll do the formula in a moment, yeah. Yeah.
A and B, that'd be potential plates or something.
Yeah, yeah. Or, well, in your case, yeah, but I mean, it just can be 2 points, yeah. They don't have to be plates, yeah. So look, if I put this coulomb here at A, and it moves down to here to B, and it gives me 1 joule, I say there is 1 volt there. Okay? But the opposite is true. If now it's at B, I have to give it 1 joule, and then it can go back to A. Okay, so if you think about your phone, okay, when you're using your phone, the energy is coming from the electrons moving around. Yes? So it's going like this. A to B, it gives you energy. But then when you put your phone, plug it in here, and you charge it up, the opposite is happening. You're putting energy inside of it, you're putting the electrons back to where they were at the start. So that's why I said it's a lot like this. Okay? You drop it, it gives you energy, and then you have to put energy back to move it to the start. Okay? So the point is, voltage and potential difference is a lot like height and potential energy. There's a similar, there's a comparison between the two. So let's try and talk about formulas now. Okay. So if we say instead of 1 coulomb, we just say Q, and instead of 1 joule, we just say W, and instead of 1 volt, we'll just say V. Let's think about the formula. If there is, well, I'll just give it to you straight. Work equals QV. So if you think about it, if I say, look, if I say there's 1 volt here, and I have 1 coulomb, how much work do I get? 1 joule. If I have 2 coulombs, I'll get 2 joules, okay? So anyways, you can easily see that the formula is work is the charge multiplied the voltage. So as you were saying then, Tal, earlier, what unit were you looking for voltage, was it? Yeah, you could say it is joules per coulomb, if you wanted to.
Yeah, everyone's asked us about the definition of potential difference.
So,
Oh yeah, that they could ask you and something like that. I mean, it doesn't have to be exactly like that. What they're looking for is for you to say 1 coulomb moves from A to B and it gives you 1 joule of energy. We say that is 1 volt. So something along those lines. Okay, so yes, this definition could be in the exam. Right, so this is formula number 3 now. But we can make a new formula because we have a formula for Q. What's our formula for Q? What does Q equal? IT. Yeah, so if I put that in there, we can get formula number 4, which is W equals VIT. Yeah. So now we have 4 formulas. Yeah. Okay. Okay, can I scroll down? Okay. Now, I don't think you're interested anymore. Huh? You know from chemistry, you have conductors, and what's the opposite of conductors? No? Insulators. So electrons can move in conductors, and they can't move in insulators. But some conductors are bad, and some conductors are good. What's a good conductor? Copper. And what maybe a bad conductor?
Water.
Yeah. Water. Water would be, yeah.
what is it?
No, water's actually a bad conductor. Yeah.
It's not that bad.
Well, not as relative. Yeah, it's not as good as copper. Yes. Yeah. But it's not actually a good conductor. Like you wouldn't really run electricity to it, huh?
Graphite.
Graphite is good, isn't it? Graphite's a good conductor. Yeah, so you have probably graphite, copper, water. And you can make water a better conductor by putting salts in it, I think. Yeah. But just, pure H2O waters. not really a good conductor. Okay. So we need to talk about now resistance. So, for example, copper, we say, has a low resistance. Graphite has an even lower resistance. And water has a high resistance. It doesn't like the electrons moving through it. So resistance can actually be defined as a formula like this. R equals the loss in voltage, or actually if you want to put it another way, the change in voltage or the drop in voltage all over the current. So what I mean by drop in voltage is that the loss of energy. And as the energy is lost, the more that's lost, the more resistance we have. That's what we say. What do you think happens to this lost energy? It's changed into what form? Heat. Yeah. So if you put electricity in copper, it might get a little warm. If you put it in graphite, I don't think so. And what about water? It should maybe even boil. Yeah. Okay, so the unit is, what, does anyone know the unit here? Ohms, yeah. That's the unit. So if you wanted a definition, 1 ohm of resistance from a material is offered. 1 ohm of resistance from a material. That means 1 volt of PD is lost per 1 amp. So you put 1 amp in and you drop 1 volt. And I'm sure someone knows this. What's the name of the machine that measures voltage?
Voltmeter.
Yeah. Hey, what's the name of the machine that measures amps? Ammeter. And what do you think is the name of the machine that measures resistance? No? What's the name of the unit? What's the unit for resistance? Ohms. So,
Ohms.
you see how the suffix meter works? Yeah. So we can measure voltage, and if there's a drop of 1 volt, and it's 1 current, then we say there's 1 ohm of resistance. So this actually gives us our next formula. R equals V over I. So V equals IR. Dun, 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 dun. Ohm's Law. So this is Ohm's Law.
We'll do resistivity.
We do resistivity, yes. Yeah. Not today, I don't think, though we will do it.
Is this a major topic in your exam? Is this a major topic in your
Yes. Major. As in, like, it's a big part of the exam. Okay, can I scroll down? Yeah? Yes? Okay. So let me just draw our first very simple circuit diagram. So we have, let's just have a battery. Hey, come on. This is a battery. And then this here is our resistance, our resistor. And what you can do is you can measure the voltage. So this is like our A, this is like our B. So this voltmeter, this tells us what the voltage is between A and B. How much of it has changed. So we know our V from this. And then we need to know the current. What's the definition of current? Yeah, well, what is current? What is 1 amp of current? 1 coulomb per second, isn't it? So our ammeter needs to measure how many coulombs are coming out of the resistor, yes? So we'll just stick the ammeter at the end here like this. Now that's actually important, okay? Ammeter, it's a bit like a speed camera. You just need it in one place and you see the electrons going by, okay? But voltmeter, see the voltmeter? It must always have 2 points. Remember? The A and the B, okay? So that's very important. Voltmeter always goes between 2 points, A and B. Ammeter, you can just stick it into the wire. So here, voltmeter, I'm like the voltmeter, I connect here and here. Okay, but then the ammeter, I can just stick it right in the cable, in the wire. And it'll tell me what the current is. Okay? Alright. The little batteries, the little AA batteries, do you know what voltage those are? The AA batteries? 1.5. You know those small AA batteries? They're 1.5. And what about the square battery?
Square.
You know the square shaped batteries?
2.5.
No, I think it's 9 actually. And you know those small circle batteries in your watch? I think they're maybe 1.5 or 2.5 maybe.
They're more than.
I'm not sure actually. Anyways, my point I'm making is different batteries have different voltages. Yeah? So you can change the voltage. So let's imagine we can change the voltage here. We can change this. If I have V equals IR, if I make the V bigger, what should happen to the I? Should it get bigger or smaller, do you think?
Bigger.
It'll get bigger. Because if you look at this here, this is a bit like, if I rewrite it, I can say I equals 1 over R multiply V. So this is like Y equals MX. So if I make the X bigger, what happens to the Y? It gets bigger. So the graph of Ohm's law looks like this. That's important. Okay, so you'll do an experiment on this.
Isn't it this voltage meant to be with 1 amp?
Yeah. Yeah, no, it is, yeah. The voltage is the one that you change. Yeah. Okay.
So R is our slope.
Actually, 1 over R.
Yeah.
Yeah, it's the slope, yeah. And you'll use that in your experiment for finding R. The reason I'm just doing this graph with you is to show you that Ohm's law isn't always true. It's only true when the heat is quite low. Okay? But for different materials, actually, the straight line isn't so straight. So sometimes you get graphs like this. Sometimes you get graphs like this. But the point I'm making is for small voltages and currents, it's true. Okay? So that's an important warning. Ohm's law is true for small V and I. Okay, so as long as it's not too big, it'll be a straight line. Okay. Now, just keep an eye on the time. Yeah, good. Okay. Can I scroll down now? So page 6. So just to be clear, resistor is the noun. Okay? So if I say this has resistance, I call it a resistor. That's the noun. R is roughly constant in each material. And this is the symbol for resistor here. It's like this. Okay. But sometimes we can change the resistance. We can make the resistance bigger or smaller. And that's called a variable resistor. Or there's another name for it as well. Do you know? Also or. Yeah, what is it? Rheostat. Rheostat, yeah. And how can you change the resistance? Well, let me give you an example, okay? So let's just say this is a big piece of copper. Can you see that here? Big piece of copper. Okay? So if I put my A here and my B here, I get resistance. If I move it down, do I get more or less resistance? More resistance, because there's more material. And if I move it here, less resistance. So in fact, all that variable resistor is doing is you change how much material the current passes through.
Why not just do it in the lab?
And that's we use that in the lab to change the resistance. Yeah. So usually what you have is, you know, if you look here, these normally look like the old ones. You have your wire coming in, okay, and then it wraps around, and then the wire comes out here. Can you see this? Look. Wire comes in, wraps around, comes out, and then what you do is there's a dial on it, you slide. So if you put it up to the top, what happens is it goes in, goes all the way around, and comes out. But if you slide it to the middle, comes in, goes all the way around, and then when it gets to the middle, it skips the end. Okay? So you see that arrow there? That means you can change the resistance inside of it. So we can vary the resistance, a variable resistor. We can make more or less. And that's what they used to do in the cinema. They had it on the wall, and the lights were bright, and then the person would come along and turn it down, or sorry, push it up, makes more resistance here. More resistance means more energy lost, which means the lights then fade away. And it's actually the same idea as well, you know, for those switches on the wall. Okay? To dim the lights, yeah. Yeah. Now, I don't think these are quite the same, but it's a similar idea. You're adjusting the resistance. Okay? So that's a variable resistor. Which, another name for that is rheostat. Okay, so let's talk about adding resistance together. So here it tells me the voltage. Now suppose I was to change this, I increase it to 20. Will this stay the same or change? What do you think?
Change.
It'll change. Because remember we have this formula, V equals I R. The R got bigger. So what happens to the B? It gets bigger also. So just be careful. What you're measuring here is how much voltage was lost. So the bigger, a big R would mean more V was lost. So this number would be bigger. Okay. if this here is R1 and this here is R2, that is the same as having one piece, which is R1 plus R2. And that's a formula. The total resistance is R1 plus R2.
In series.
Very good, in series. But it's not the same situation if you put them side by side, parallel. Can I go down? Yeah. So if you have them like this, here's your wire, then it splits, and then this is R1, and this is R2, and then it comes back together. It's not the same. They don't add as simply. You have this formula. 1 over R equals 1 over R1 plus 1 over R2. This is, now we're on to page 7. So this one is when we say they are parallel. So I think we should do an example of this now. Yes, let's see. I'll just make up my own example. So can I scroll down? Yep. Okay. So this is 5, and then this one here is 6. So the total is 1 over 5 plus 1 over 6. Okay, what's that? We'll have to work it out. This would be 30, wouldn't it? So, yeah. You give me the final answer or part of it? 6. Okay, thank you. 11 over 30. So then R equals 30 over 11. Okay, so that's not so bad. So what I'm going to do is I'm going to draw a diagram, and I want you to tell me the total resistance. I'll add many parts to it, make it more interesting. Okay. So I'll split, then I'll split again. And then I have one here, one here, one here. And then I have one here, one here. How many do I want to add now? And then the 2 together, and then one more. Yeah, why not? And I'll make it easy, okay? I'll just say they're all 2 ohms resistors. So these are all 2. So I'd like the total. So first you should add the series ones together. So I'll just give you the steps, then you can do it. So you should do these ones first, add them together, and then use the parallel formula to add both of these together, and then the big one at the end. All of this together with this one at the end. Okay, so you have to do it bit by bit. Alright, I'll let you try it, then I'll do the answer. So give me the total resistance here. They're all 2. Each resistor is 2. One, 2, 3, 4, 5, 6, 7 resistors in total. Yeah. You have the answer now? Yeah, we'll do it now in a second. There's a 2 at the end, yeah. Do you have the answer? Okay, let's have a look at it. So let me add these two together. So if you want, we can draw it as well. Are you looking? Look. These two go together, and how much is that? 4. And then these two go together, and that's 4. Now this is a 2 and this is a 2. So 1 over R equals 1 over 4 plus 1 over 2. So that's 3 over 4, isn't it? So then R equals 4 over 3. So that means, look, this here is 4 over 3, and then this here, what's wrong? Okay, but this is right so far, and this is 4 over 3, and then these add together. 1 over R equals 3 over 4 because it's 1 over, plus 3 over 4, so that's 6 over 4, which is 3 over 2.
Plus 2.
And then, yes, and then this piece here adds together with this piece. So plus 2. 3.5.
You need to
Yep.
reverse it.
Oh, that's true.
Oh yeah, sorry. Yes, you're right. That's for 1 over R. So then R equals 2 over 3. So this is actually 2 over 3, and this here is 2. So plus 2. So 2.67. So that means that whole diagram can be replaced by just this. 2.67. It's the same thing. That is very important for the exam, because often in the exam you have these big diagrams and you need to simplify them before you can do the question. So my big diagram of resistors became just that one resistor at the end. Okay, so that's an important skill. Okay. Let's see. Okay, so we're going to do some more circuit diagrams now. Just before I start, I want to make one point made clear. This formula V equals IR. Okay? I think to prevent confusion, I'll just say, to be safe, only use this formula on one resistor. So what I mean is, when you're using this formula, you need to only use it in this situation, where you're looking at the voltage between A and B when it's on one resistor. The reason I'm saying that is because students sometimes make mistakes using this formula. So it's easier for me just to say, use Ohm's Law when you're dealing with one resistor.
Isn't there an Ohm's Law for a circuit?
Yeah, we can have, there's other formulas too for when they're more complicated, yes. I'm just talking about V equals IR. Really, to be safe, only use that when you have one resistor. You're talking about one resistor, okay? So this is the voltage between A and B around one resistor. Okay, so let's have a look now where we have to use V equals IR and our other formulas. Okay. Can I scroll down?
Yes.
Yep. Okay, let's draw a diagram here. All right, well, we'll draw this. Okay, so here's our power. Here's resistor 1, here's resistor 2. And you can just, the current we always say the current goes from positive to negative. by the way, I'm sorry, I didn't tell you this in the last diagram. Where's my battery gone? Oh, I didn't draw it. I'll show you in a moment. Okay, and here we'll call this big voltage here V, like it's a battery or something, or it's on the wall or whatever. I would like people now to give me a formula for, let's say, the I. So I want you to tell me what the I is. Now, what formula can you use to get the I? Yeah, V equals IR. But what did I say about that formula? One resistor. So first, what you need to do, put them together. Then use the formula. Okay, so just tell me what the I is. Yeah, no, it won't be a number. You give it to me in terms of V, R1, R2. Yes. Yeah. That's it, yeah. That's it. So what's the total resistance here? R1 plus R2. So you have V equals R1 plus R2 multiply I. So we have here I equals, as you said, V over R1 plus R2. Okay, now let's imagine we put a voltmeter here, and I call this one V1, and I put one here, and I call this one V2. Can you give me a formula now for the, what would I like? Yeah, but the V1. What's the formula for V1? I equals I multiply R1. And here, I multiply R2. Now, here's my question. Are those I's the same, or are they different? Why?
It's the same.
Yeah. Well, remember what the definition of current is. What's 1 amp of current? 1 coulomb per second. So if 1 coulomb goes through the first one in 1 second, then in the next one, 1 coulomb went through the next one as well. It's like people walking down a hall. Yeah. So if 1 coulomb goes through the first one, another coulomb goes through the second one.
But it doesn't apply that way on parallel circuit.
No, it's different. Yes, you're absolutely right. If the cable split, then in 1 coulomb, or well, 100 coulombs, so many go one way, so many go the other way. But
It depends on the resistance.
exactly right, yeah. But if it's just a straight line, then there's no choice. So we know those I's are the same. Yep. And what do you think? Is that I the same as the I over here? It is, isn't it? Because it's all just one simple loop. So all those I's are the same. So we could put these together, which is what I want to do. So what I want to do is I want to get rid of the I's here. So I replace the I's with this formula here. So I get V1 equals R1 over R1 plus R2 multiply V. I'm taking this and I'm putting it in here and putting it in here. And then V2 is R2 over R1 plus R2 multiply V. Why is this useful? Well, this is actually a special type of circuit. This is the reason I'm doing with you. This type of circuit, the name for this one is called a potential, well, maybe someone knew it already, divider.
What's the V doing there? R2.
Which V? Here?
Yeah.
Oh, well, I'm subbing this in here, so now the V goes in there. So I'll give you an example, or I'd like you to do one for me. Let's say here is 100 volts. And then let's say this is a 5, and then this one here is a 10. Can you tell me what the V's are? As an example. So can you do that now on your calculator really quick? 66 and 33 roughly.
Yeah.
Yeah.
There's a difference between.
Yeah, for the first one,
Yeah.
and then 66, yeah. So roughly 33 and 67 then. Now this is called the potential divider because that's what it does. It takes the voltage and divides it into two. So in this example here, how big is my battery? It's 100 volts. And I've made a part have 33 volts and another part have 67 volts. What do you mean how?
Like how did you make it 5,000?
Well, yeah, you see, oh yeah, I just measured it. So then if I took the voltmeter away and connected something to it, like a light bulb or something, then the light bulb would have 33 volts and then the other light bulb would have 67. Okay, why is this important? Well, if you think about something like your computer, okay, does anybody know what voltage you get from these plugs here? 220. But when you think about your computer, there's many different parts. And does each part need 220? No. The screen would need more than the processor. Okay? Processor probably only needs like 1 or 2 volts. Yeah, the processor is low. The screen would need more. So you sometimes need to take your 220 volts and then share it between different parts. And this is a very, very simple way to do it. Okay? You put the resistors, and then you can connect around the resistors. And each resistor has a different voltage going through it. Okay? What do you think would happen if I replaced the 5 and 10 with 10 and 10? They'd have the same voltage. Yeah? So what's important is how big they are compared to each other. Yeah? So if it was 10 and 10, there's no point. They'd each have the same voltage then. Okay? So this has been on the exam, and it is in the syllabus as a circuit you need to know. You need to learn this one. This is called the potential divider. Okay?
The resistance was 1 ohm. Would it be higher or more for voltage?
Which, in total or for each of them?
Yeah, for each of them.
If they're both 1?
Yeah. No, if R1 was 1.
Oh, if R1 was 1 and R2 was still 10,
Yeah.
then those numbers would change a lot. So I think it'd be like 10 and 90 then, 10 volts and 90 volts. Yeah. But like I said, the important thing is not how big they are, but how big they are compared to each other. So if I replace this 5 and 10 with, let's say, 0.5 and 0.10, 0.05 and 0.10, it's the same. Because it only matters the relationship to each other. Yeah. So do you think you would want to use big or small resistors for this circuit if you want to split your voltage? Small. Why small?
It is safe.
True, yes. But why in this case does it matter?
Reduces the voltage.
Yeah, well, remember I said...
But
remember I said about Ohm's Law. When can you use Ohm's Law?
Small
resistors. Small voltage. Well, small resistors, really. Okay? So here, if I want this result to be true, if I use a smaller resistor, it's going to be more accurate. And also cheaper as well. Okay. Let's see. Okay. Oh yeah, and also, notice this. If you add the two voltages together, what do you get? 100. Which is how much the battery is, isn't it?
Yeah.
That's actually a rule. That if you add up all the voltages, it should total the 100 battery.
Why isn't that wrong?
Hmm?
Isn't that wrong?
What do you mean?
Current is lost by heat. Required.
Yeah. Oh, but yes. But remember, these 33 and 67, that's like the voltage that's being used up. So what you're really saying is the battery has 100 volts. It goes around, it loses 33, it loses 67, and when it gets back to the start, it's at 0. There's no more work it can do. So when it goes around, it does all its work and gets back to the start. There's no work left, and then another charge comes out. So yeah, these are losses. So 100 comes out, and then 100's used up. A bit like with the energy. Energy at the start equals energy at the end. Okay. I want to do some questions. Hold on. I want to do some examples. Let me think. Which one do I want to do? Right, questions. Okay, so I just have one more thing to say. I'll do an example, then you can start on some homework questions then. Okay, so Tanis, you were mentioning earlier about the current when it splits.
Oh, yeah.
So if you remember here, look please, if this is I, and then this one here is the next resistor, it also must be I. They must be equal, because if 1 coulomb a second goes through this one, then 1 coulomb a second must go through this one. What would happen if there was less than 1 coulomb per second here?
Where?
In the second one, if this was smaller than 1, what would happen? What does that mean is happening? It means the electrons are building up. Think about a room. If 10 people go in, and then 5 people come out, what's happened? 5 people are still stuck in the first room. Okay? So it must be the same so the current can flow. But as you were saying, Tanish, if it goes like this, if it splits, this is I, then these are not the same. This would be I1, and then this one here, I2. But what you do know is I should equal I1 plus I2. Why? Why do I know that? Well, again, like at the room, if 10 people go in and 2 people go to the left, then how many people must go to the right? 8. And if it's 10 people per second, then it must be 2 people per second and 8 people per second. Because again, if it was not, then that means people are building up. Okay? What's that?
How do you get I1?
Oh, well, that's what I'm going to do next as an example then. Okay, so let's have a look. So if you look at page 21 then, have a look at page 21. So as an example, I'm going to do number 7 on page 21. Can you see that? Yep. Okay, so 2 resistors of 3 and 6 ohms are connected in parallel across a 6 volt. So it's like this. 3, 6, and then the voltage is, what does it say? 6 volts. What would they like? How I1 and I2 are related. Okay, so let's add these together.
Is it the same ratio as the resistors?
Yeah, it'll be a ratio, like in the potential divider. 1 over R, is 1 over 3 plus 1 over 6. That's a half, isn't it? No. Yes. This is 2 sixths plus 1 sixth, 3 sixths, a half. So then what does R equal? 2. So you know that this is the same as this situation. 2. And what's the voltage here? Still 6, isn't it? Now, can I use this law? Yes. V, 6, I, we don't know, or 2. So therefore, what does I equal? 3 amps. So this here is 3 amps. And here, how much? 3 amps. But here they split, and then they go back together. So if I have I1 and then I2, what do I know about I1 and I2?
I plus I1 plus I2.
Yeah, I1 plus I2, what should that equal?
I1.
I, which is 3. So that's the first relationship, that I1 and I2, they must total to 3. Is that what they want? Let's see if they go with that as the answer, 7A.
No. They want to hear that I2 is twice bigger than I1.
Oh, they don't just want a plus, they want to know how much compared to each other. Yeah, okay. We'll do that now. Alright, so I have a little bit more to do on this, but let me just check what they wrote here. What chapter number is this? Chapter 4? Oh, no. The answer is even simpler at the back. At the back they just said I equals I1 plus I2. So we've actually done a little bit better than at the back. Okay? So that is fine then. Alright. The next part is what is the potential difference in each resistor. Okay, so let's look at the first resistor, the tray. We know what the current is. What's the current? What did I say the current was? It was 3 also, actually. Yeah. So the R equals 3 and the I equals 3. So what does the V equal? V equals I R. So that equals 9. Now let's look at the other resistor. So the resistor here, what's the other one? It's 6, isn't it? Okay. And then what is the I? It's also 3. So then what's the V? IR, which equals 18.
I thought that the I should be different. Yeah, because they are in parallel.
Ah, rats, they are. Thanks for pointing that out.
So the lower I is 2, the upper I is 1.
Yeah, but I don't know that yet. Sorry. You're right. Undo. Alright, let's go back. Sorry, so what is the same? The current is different, but the voltage is the same. Yeah, the voltage is the same. Which do they give us in the question?
No. Yes, they do.
Do they? Oh, great, they do. Oh, yes. It's right there, 6 volts. Sorry, I'm being a bit of a moron. So, back to the question again. Resistance is 3 and the voltage is 6. So, V equals I or, so the I equals V over R, which is 6 over 3, which is 2. Great. And then in the other one, R equals 6, V equals 6. So again, what does the I equal? V over R, which is 6 over 6, which is 1.
Which adds up.
Which adds nicely up to 3. Yeah?
What if you use the method of potential by 3 over
These aren't in series, they're in parallel. That's the difference. Yeah. Someone said something? No. So what does I1 equal? 2. And what does I2 equal? 1. So the total is it 3? It is. Okay. So I've actually done A, B, and C. Now on to D. Is 3. D is find the single. Oh, I've actually done D already. What's the resistance when you add together? Which is how much?
2.
What did I say? Where is it? Did I there, it's 2. Yeah. So I've actually done the question completely backwards. I did the D part first. Yeah. Which is 2. Oh, so I finished the question there. So the question was, what is the total resistance? What is the total current? What is the current in each part? And what is the voltage in each part? And just before I do the homework, I just need to say something about voltage again. So current, if I have 2 resistors back to back, is the current the same or different? The same. Then if the current splits, are they the same or different? They're different. Now, voltage is the opposite. Listen, voltage is the opposite, okay? So, if I have voltage like 6 volts, and I split it, how much is in each?
6.
Still 6. It's the same, okay? But, if I have them back to back, they add. Okay, now how do you know this? I'll give you an example. You know you've got your battery, like an AA battery. How big is this? 1.5. Okay, so if I put a 1.5 battery with a 1.5 battery, in total I have like a 3-volt battery. Now when you put your batteries in like your camera or whatever, you put them in like this. Are they in parallel or series? No, they're actually in series. Because you put one battery up, don't you? And then what's the way you put the next battery? Down. And then the next battery? Up. They always switch. That's because the current is going like this. In the first one, down the second one, up the next one. So this is why they must be opposite. Because they're really actually in series. So if you have 4 1.5 volt batteries, what's the total? 6 volts. And then what? If I have 1.5, negative, positive, negative, positive. Which way do I put them together? Positive to negative, don't I?
Yeah.
So what do you think happens if I turn this one around? Nothing. Okay, so look. This is 1.5. This is 1.5. But if I turn this one around, it's minus 1.5. So when I put them together, 0.
They can't do anything. It's
Nothing happens, yeah.
minus and plus. They can't do it.
Yeah, so when they're like this. So when you put batteries together, the positive must touch the negative end of the battery. Okay, so just to say it again. Current, straight line, A and B, same. If they split, not the same. Voltage, if they split, same. And if I have my batteries, for example, together, they add together. Okay. So if you were to look back at number 7 here, here's the battery. You see the little arrows? It's going around this way. Look up. It's going around this way. So the I splits. 7, the one I was doing. But the 6 volts is still 6 volts in each of those.
Yes.
But if I put these resistors back to back, will it be 6 volts in each? No. And then that is the potential divider, which we did earlier. when they have back to back. So the voltages are different. So maybe like 4 and a 2. Oh yeah, it would be 4 and a 2 because it was a 2 and a 1.
Sorry,
Yeah.
could you repeat what you said?
Which part?
The
About the voltage.
potential divided.
Yeah. Oh yeah. These are in parallel, aren't they? Yes. If I then move this to here to make it in series, then it becomes the potential divider problem, which I did a moment earlier. Yeah, what's wrong? Oh, we're happy with that, right?
Yes, it's amazing. Cool.
It is
Cool stuff.
No.
So we're hungry.
Okay, so am I. Now, what I want you to do, listen. I think 1, 2, and 3 are more just basic questions. No, don't do 1, 2, 3 because I think they're just basic questions. What's really hold on. What I really need you to do is the circuit ones.
Just 8.
I've already done 7. So 4, 5.
8.
Stop saying numbers. Just listen to me. 4, 5, 6, 8, and 9.
So the next week?
Just listen. When do you have your physics test?
Thursday.
Thursday, isn't it?
Yeah.
Isn't that what says in your timetable?
Wrong.
Yes, yes.
It's definitely Thursday.
It's Thursday.
Yeah. So look, I still want these done for tomorrow because you had your week off to study physics, okay? And don't worry then, tomorrow the homework can be due for the following week because I know you'll probably want to do some work tomorrow night. Tomorrow's Wednesday and the exam's on Thursday. But you can do some work on this tonight. So I want these for tomorrow.
Okay.
Okay, but don't worry, tomorrow's homework will be for next week.
Thank you.
Okay?
Thank you.
So,